Hello again, this is Mr. V. Hill, and today we're going to be talking about exponential growth models. And we're just going to start with a little example here of exponential growth, this being a bacteria population. And this population grows at a rate of 7% per day, and we're going to start with 50 bacteria in a petri dish. So, just to examine how this is going to behave, let's first make a little table of the number of bacteria versus day. So just like we did with our exponential patterns way back when, we're going to start with day 0, being the very first day we start in introducing the 50 bacteria. We could call it day 1 if we wanted to. Mathematically, it doesn't really matter, but I think this is going to help us stick with what we had before, and also it's nice to be able to see this y-intercept right here, because day is the independent variable and the number of bacteria are the dependent variable. So when the x, or the independent variable, is 0, that's really talking about our y-intercept. But then after 1 day passes, then we're going to increase the population of bacteria by 7%. And so if we wanted, we can break out our calculator. And so we're going to gain 7% of these 50 bacteria that we started with. So since 7% is 0.07 written as a decimal, type that in, and we're going to get 3.5 more bacteria. Now, of course, we can't have a half of a bacterium, but, well, this is just a model. So everything's kind of just approximations. It's giving us an idea of how we might project into the future and how many bacteria we're going to have. So, of course, we add those 3.5 bacteria onto the 50 that we started with, and that leaves us with 53.5 bacteria after 1 day. After 2 days, we're going to gain another 7%, but not 7% of the original 50. Now we're gaining 7% of the 53.5. So we take 53.5, multiply that by 7%, and we get 3.745 more bacteria, which of course we need to add on to the 53.5 that we started with, or that we had before on day 1. Of course, giving us 57.245. Again, these are not exact numbers or anything. This is just a model. After 3 days, we're going to gain 7% of this 57.245. So we multiply that by 0.07. Then add that back to our 57.245, giving us 61 point, and now we're going way too accurate here. We certainly do not need to go out this far, since it is a model, and then you can't have 0.25215 of a bacteria, right? So that's the basic idea here. But we need to see how this process is really working. So what we want to look at really is how we got this 53.5. The 53.5, well, it came down to, we had our original 50, and then we added on 3.5. Right? That was our 53.5. That's how we calculated that. But this 3.5 really came from multiplying 50 by 7%, or 0.07. And this original 50, if we wanted to, we could just say, well, that's really just 50 times 1. But now what we want to do is think about the distributive property. We have a common factor of 50 here. So if we put parentheses around the whole thing, and then took this common factor of 50 in both terms, and instead of distributing it, we undistributed that 50 out to the front, well then, what we end up with is, we have that common factor of 50 out here, and then inside we have this one, our plus sign, and 0.07. Or This is 50 times 1.07. So multiplying 50 by 1.07 brings us to 53.5. Now if we take a 53.5 and multiply that by 1.07, yep, that gets us 57.245. Multiply that again by 1.07, yep, 61.25215. So what's going on here really is we're starting with this value of 50, and then the pattern is that we're going to multiply by 1.07 to get to the next stage. If we wanted to, we could write a recursive rule for this. So remember, the recursive rule has to include what we're starting with. So we start with 50. And then to get to the next stage, we're always going to multiply the previous stage or previous value by 1.07. And if we remember from way back when we did our exponential patterns activities, we can then turn this recursive rule into a general rule. So first we have to define some variables. So we'll let x be the number of days that have passed, and then we'll let y be the number of bacteria. So what we end up with is y is going to be equal to the starting amount, 50, and then the repeated multiplication becomes an exponent. Because of course 53.5 is 50 times 1.05. 57.245 we'd get by taking 50, multiplying that by 1.07, then multiplying that by another 1.07. Okay. So 1.07 squared, and so on and so forth. So where the number of days that have passed is the exponent. Or, if we wanted to, focusing on the increase of 7% each day, we could write this as y is equal to 50 times, instead of 1.07, we could write 1 plus 0.07 to the power of x. This equation up here is just focusing on the fact that we're multiplying by 1.07 each time. This equation is focusing on the fact that we're gaining 7% each day. So the general exponential growth model is exponential well, it just looks like this. Y is equal to a times b to the power of x, where a is the initial amount and b is what we call the growth factor. Factors are, of course, things that we multiply together. So we're multiplying by b over and over and over again. That b would be like the 1.07 up here in our example. Or, if you want to write it this way, y is equal to a times, instead of b, we'll write it as 1 plus r to the power of x, where r is what we call the growth rate. And so the whole idea is just that the growth factor b is always equal to 1 plus the growth rate. So just whichever way you want to focus on, either on what we're multiplying by each time or how much we're increasing by each time. So for our example, the initial amount, A, was 50. The growth rate, B, was 1.07. the growth factor was 1.07, and R, the growth rate, is 0.07 or 7%. So let's see what we can actually do with this model now. Again, y is equal to 50 times 1.07 to the power of x, where x is the number of days that have passed, and y is the number of bacteria. So suppose we want to know how many bacteria will be present after, let's say, 15 days. Well, this is pretty simple here. X is the number of days, y is the number of bacteria. All we do is plug in 15 for x, calculate y. So y is equal to 50 times 1.07 to the power of 15. And we get 137.95, so approximately 138 bacteria. Again, we're only going to get estimates out of this because it's just a model. It's not exact at all. So that's one question we might be able to ask. Another one would be, perhaps, how long will it take to get, let's say, I don't know, 200 bacteria? Okay. So what we can do here, I'm just coming up here to give myself a little room, starting with our model again, y is equal to 50 times 1.07 to the power of x. Now we want to know when the y is going to be 200. And we need to know what the x is, how many days. Essentially what we're trying to do is we need to solve this equation for x. Of course, we solve just by undoing what's being done to the variable in reverse order of operations. So the first thing we need to do is undo this multiplying by 50. So we divide both sides by 50. 200 divided by 50 is, of course, 4. Now this equals, those cancel out, 1.07 to the power of x. Now we just need to undo this exponentiation. But how do we do that? So we need a way to undo an exponent. And there is a way to do that. And that involves a little something called logarithms, which is really just the inverse of an exponential. But you're going to get that in Algebra 2, and I'll leave that to your Algebra 2 teacher. Instead, what we could do is make use of our handy-dandy calculator again. So if we go over here to our function y equals screen, we can just plug in our model. Y is equal to 50 times 1.07 to the power of x. And we want to see, well, what value of x will give us a y of 200. The table is a great way to see that. So at 0 we have 50, at 1 we have 53.5, 6 days are up at above 75. So let's just scroll down here and keep going and going and going and going and going until we see, oh, there we go. After 20 days, we have 193.48 bacteria. Right? So again, this is just approximate. After 21 days, we have over 200. So according to the model, it is going to take somewhere between 20 and 21 days. And that's pretty much it for basics of exponential growth models. We'll do a bunch more practice in class. But for now, I'm going to leave you with a cute little Scottish Terrier puppy dog.